Hello. It's been a long time between updates for the EMS Spectre clone project, but don't let that trick you into thinking that I haven't been working on it. I have. I just haven't been making videos about it. I'm eating a delicious mushroom bowl, and it is very cold at nighttime here. So, I moved from looking at the internals because I've been doing that for just a bit too long, and I was just getting a bit, in my head about it, to more of the larger kind of architecture and the hardware interface. So I made this little prototype board that plugs into the back of my RT-Z7 zinc board that I was using. So the FPGA is on the whiteboard here. So I made a little interface that, upside down, that let me try out a bunch of code that I'd made. So some multiplexed buttons. We got lots of button controls. These are all endless rotaries. And then these are analog inputs. So these would be knobs, sliders, or CVNs if they got buffered with a op amp to kind of protect the FPGA input. So one of the things about rotary encoders, buttons less so, but one of the things about rotary encoders is normally when you use them with a microcontroller or something, you run into this bottlenecking problem of the more rotary encoders you have, every time a rotary encoder changes, you have to typically use interrupts to detect change. Then you have to read the two signals that come off the rotary encoder to work out which way it's turning and how many turns and blah, blah, blah. And so those normally happen as interrupt sequences. So turning a whole bunch at once can cause lag in other places, or there's kind of a limit. Anyway, I wanted the design for the EMS Spectre clone or its hardware interface to be kind of processor agnostic. And so the way that the rotary encoders on this work actually is that each of them has their own little state machine and their own bank of registers that can hold values. So the idea is that without any external processor required, when you turn the rotary knob, it adds and subtracts the number of clicks or the number, the value that you're changing to a register. And it has each of these in the code that I've written on the FPGA has banks of registers. So that means that when you do something like change a page, or when you do something like go to a different function, even that doesn't need the processor, because once you change the page or the register or whatever that the rotary encoder is writing to and reading from, it's like having a tiny little processor for each of these rotary encoders, but it only does one thing, which is read the encoder and do addition and subtraction. And so what's really nice about that is without a processor, you can get all these values really easily. You don't need to have the processor stop and do stuff and blah, blah, blah. So that's super nice. I was doing some tests to work out if the scan time on being able to scan all the buttons and read button presses is good. That needs a little bit of work still. So that's in the works. The analog stuff, I think I'm actually going to use a separate microcontroller to handle all the analog stuff and just have it pass that data to the FPGA, because there's a bunch, you can do analog stuff on Zinc FPGAs, but it was just a bit, one thing is it was going to mean that the design with the analog inputs was going to be locked to Xilinx FPGAs, and that maybe that's something that has to happen, but I'd rather it happen at kind of a later stage. So at the moment, I'm thinking I'll use a Raspberry Pi, like the R1 microcontroller, it's called Pico, R1 Pico microcontroller, to read the analog signals and then just over an SPI bus right to the FPGA. I think that's going to handle stuff. And so actually, I need a, I'm going to need a microcontroller or in the design as well. Anyway, and I will tell you why. So my current development stuff, I've been using a Zinc. So Zinc is a very kind of top tier-ish FPGA from Xilinx. It's got a dual core ARM processor in it. They're very expensive. They're very expensive, and it's way more than I need for this project. So, oh, and they're also like very difficult to design with, to design boards with, because there's just so much other stuff going on. So I wanted something cheaper, and I came across, after a very long search, this dev board from QM Tech. Actually quite a reasonable price. I think they're about 50 Australian dollars each. It's got actually an RTX. Can I focus on that? It's got an RTX A7, RTX 7 on it, rather than the Zinc. So RTX is kind of the tier below Zinc. So normally it goes ultra scale, RTX, ultra scale, Zinc, RTX, Spartan. And there's some other stuff in there, Kinects and with different architectures. But the main thing is that this is a board that is going to be cheap enough to clip into an existing design. It means I won't have to dedicate a lot of time and money to designing my own version of this board and the layout and making lots of mistakes with that, which I inevitably will. The downside to it, though, is it's got a little ROM chip here, which is where it stores the program. So FPGAs are blank at startup, most of them are blank at startup, and when you boot up, it needs to load its settings. And so in a lot of cases, that will come from a little, EEPROM that you stick off to the side. And so when it boots, it requests, it starts putting out a clock, and this EEPROM will feed back what's called the bit stream, which is the internal settings. And so it'll so what my plan is for this board is to use pogo pins from a board mounted on top that touch these pins, which will mean that from another microcontroller, probably this Raspberry Pi Pico 1, you will be able to have updates. Because the way that you update, so the way that you would update this, even though it has a USB port, this is just for power. The way that you would update this is you would need to connect with JTAG using these pins here. You need a JTAG adapter. You then would need the software capable of communicating via JTAG. You would then need a programming file to live on the ROM. You would then have to load that programming file onto the ROM. So there's just a lot of kind of stuff going on there. And setup and process, like, no, people don't want to do that shit. People just want to, get an update and have it just work, kind of like by magic. So the hope is Raspberry Pi RP1 with an SD card slot. When you want to update the design, when you want to like update, and I imagine there will be updates, because nothing is ever right the first time. And one of the great things about FPGAs is that you can do in the field hardware updates. So the Raspberry Pi Pico will read from an SD card. The SD card will contain an updated bit stream in a binary format to go on the EEPROM. Raspberry Pi Pico reads that, checks that it's all good, takes the FPGA, turns it off, stops it from loading, and in that state, it's now disconnected itself from the EEPROM pins, which means that the Raspberry Pi Pico with those pogos that come down from a board that's mounted on top can program that EEPROM, and when that's done and it's checked that it's all worked, can release the FPGA so that it boots up, it will come to life and now read the new updated program. Hello, George. Would you like to say hello? Oh. So, yeah, so the developments that have been happening have much more been in the hardware interface space. So looking at what kind of interfaces I need, what kind of programming inside of the FPGA I need to interact with these interfaces, finding a suitable dev board. One of the good things is that this company makes similar sized dev boards with a couple of different Xilinx FPGAs on them, which is great, because the one on this particular board is very small. It's an A15, which I think is the second smallest, but it looks like it looks like all of the code that I've written so far will fit on there. That doesn't look like it's going to be a problem. That's all in a great state. I've been running a bunch of tests to see what the power consumption is, and whether or not it's going to need heat sinks and kind of like a cooling system and stuff. And it seems incredibly unlikely at the speeds that I'm running and with the kind of things that I'm doing, the amount that I'm driving. Yeah, it doesn't really seem like it's going to need any kind of active cooling, like a fan or anything. And if it needs a heatsink or something, that would just be like a kind of peace of mind thing to handle maybe hotter environments, where the ambient temperature is, 35, 40 or whatever. So going to keep on top of that as this develops further. But yeah, for now, that's probably all the updates I've got. And there's definitely stuff still moving. It's just been moving a bit slowly. It's just, slow is the wrong word. It's been moving in a way that is less easy to show, like visibly and interestingly, what's been happening. Like I could show a spreadsheet that shows power utilization based on the current design, but that is batshit boring. And I could show myself searching AliExpress for hours looking for, Xilinx dev boards, but also batshit boring. Anyways, stuff is happening, stuff's been going, it's all moving in the right direction. And yeah, pretty soon I'm going to start compiling everything together to put on this new Artix dev board. And I'm in the process of designing a new front panel to go on that will have more of the final kind of interface that I'm imagining. Things like a little LCD to preview your video out, HDMI connector to stream the video out, and part of that will be seeing what kind of resolutions and speeds we can actually get out of this kind of a design. It's definitely going to be, no, I'm not going to say that. I'll cut that out. Yeah, everything feels like it's humming along, so stay safe. Stay tuned, check out the previous videos if you want to see visual examples of what's actually coming out of the designs that I have so far. Yeah, I think that's everything. So till next time, bye.